the key technology of WAN interconnection. So we'll talk about the detail of technology which will be used in the WAN connection. Okay, so in the WAN interconnection, there will be a lot of different type. The technology will be used. So on live network, the GRE and the LGTP, those two technology will be used as a networking technology. And IPsec most of the time will be used with them. And also in the live network, some WAN interconnection are located behind the NAT device. So we also need to use some technology that to provide the NAT traversal. Okay. And to ensure the reliability, we also need to have some other technology can help us to detect the connection to select the best path. Okay. So on completion of this course, you will be able to describe the working principle of the common WAN connection technology and the working principle of the IPsec. And it also will be able to describe the common solution and the basic principle for NAT traversal. And also you will know how wide area interconnection intelligent traffic steering works. Okay, so let's look at the networking technology in the WAN interconnection first. First, we talk about GRE, a very simple one. And so a little bit background that for some company that if they want to create the communication between branch and headquarters, and if you do not purchase that private line, you think the private line is too expensive, you only purchase the internet. Okay, in that circumstance, you can use GRE to create the WAN connection between your branch and headquarters. Okay, to like this. This is background. So for the idea of the GRE, it's very simple. Like for example, you want from here to send to here, from one inner network to another, one internetwork to another internetwork. You need to create some tunnel, right? You need to create some tunnel. So the GRE basically is a tunneling technology. So for tunneling technology, the working concept is a very The working concept is very simple. It basically is a like out header over inner header, right? And this, for example, you want sending from here to here and to inner header, and you create another out header. So those out header will help you forwarding the packet from one devices to another devices. And when it reaches to another devices, it will decapsulate the out header and use this in the header to continue to do the forwarding. This is tunneling. No matter you are using GRE, VXLAN, MPLS, and in the later segment routing, V6, SRv6, those tunneling technology, they have the same concept. Put another header before the inner header. That's all. Nothing different. So GRE basically have the idea of the GRE is the same with the tunneling technology. And GRE is a layer 3 technology. Layer 3 technology. Okay, so this is GRE header looks like this. 32 bits long, and there will be few field is important. One is C. C means check whether I should do the checksum or not. Checksum is a security feature. Another is key. Key is also another security feature. Okay, those is two is security feature. Checksum is to detect whether your packet is being modified or not. Okay, and key is whether I can receive can be decided to whether I can receive this packet or not. I can process this packet or not. Okay. So two features. And let's look at the what is GIE? How is GIE forwarding packet? So as we said, the GIE is a tunneling technology. The working principle is same with tunneling technology. So we can say, for example, I want sending from the IP1 to the IP2, so I'll create the packet, source destination, IP1, IP2, and then send out. And when the packet is going to the device A, and this device A have interface IPA, address is IPA, another side is IPB. So I'll put the out header before the GIE header, before the inner header, and from A to B. And here is the internet. So I'll forwarding out to the B, and when the B reach it, it looks like okay, the destination is B. I will decapsulate the packet, and it's a GI packet, and continue to decapsulate, and the inner header will be S1 to IP1 to IP2. So we'll continue to send to the destination. GIE, very simple idea. Okay. So for the GIE, the idea is simple, nothing difficult. Let's look at a little bit of feature for the GIE. First is a keep alive detection. The GIE is very simple to forwarding the packet, but for the GIE, it cannot detect whether my connection is okay or not. It cannot detect it. Although it's a GIE tunnel, but I cannot detect it by default. So you can use this keep alive detection. Just sending a keep alive packet to see if there's a reply or not. And if there's a long time no reply, and I will consider your timeout, a timeout. But if inside the timeout timer, there's a GIE keep alive send to me, and I will know, okay, there's the other side is okay. So I will keep GIE channel up. Okay, simple idea. Another is for security mechanism for the GIE. As we said, the GIE, for the GIE date, there will be two type of attack, two type of risks. First is that the GIE data might be modified. So when it's sent to another side, because GIE by default there will be no encryption. There's no security feature. I mean, cannot be encrypted for GIE by GIE itself. Anyway, so there will be a chance that your packet will be modified. Another is some packet are trying to send in to you some packet, but it is not allowed because I am not going to create the GIE tunnel with you, with this attacker. So those will be two risks for the GIE tunnel. The solution for the security is like this. First, we can use this checksum. Checksum's idea is very simple. It's like, for example, when the first time when the packet was sending from A to B, so the device A will create the packet and put a checksum into it. And this checksum actually, you can consider it's an MD5, the hash calculation. They are doing hash and trying to create some value for the checksum, and it will send it to another side. And when it is going to the B will also doing the checksum calculation again. And if the device B, when they're doing the calculation, the checksum is B, and for the A, the checksum is still A. So they are not, they are inconsistent. So I was thinking, okay, this packet is being modified. I should discard this packet. So this is for the security feature for the GIE. one security feature. Another is for key. Key is very simple. I just put first this flag will be set to 1, and the key have any number you want, for example 100 or maybe 1000. For example, in this example, it's a 10. And if there's some packet sending to me and the key, this is in the GI header, the key is 20, it's unlike the key I configure locally. In local database, the key is different. So I will not receive your packet. I will not process this packet. I will directly discard the packet. Okay, I will discard the packet. So this is a GI key. This is prevent some attacker to connect it to me. Okay, this is GI. So for the GI using scenario, application scenario is like this. First, when you create the GIE, you actually can create the OSPF neighbor relationship between your headquarters and between the branch. So basically, the error for the OSPF should be like this, like error 1, 2, 0. Here is 0. So here is 1 and 2. So it's like this. Because GI internal can forwarding the multicast packet. And also there's some other using scenario is GI over IPsec. This is widely used in real network. Because how do I say this? The GIE is can forwarding the multicast packet, but the GIE cannot create any security feature. There's no security feature. I mean, the GIE cannot. The technology itself do not have the encapsulation encryption feature, so they need to use some other technology, is IPsec. Okay, about the IPsec technology, I will talk a little bit later. But IPsec itself cannot forwarding the multicast packet. So when you combine them together, which means you can forwarding the multicast packet inside the GI tunnel, but outside you can covered with the IPsec tunnel, the GI over IPsec. So that will be very secure, and also the network will be much more easy to create. Okay, the GI over IPsec, widely used this one. Okay. And here is also some other using scenario is how to help the MPLS VPN network. Okay, so in some using scenarios, some customer may be facing this situation that the customer between them, those is not MPLS network. Those devices do not support MPLS. So those customers just purchase the internet, and but those packets, they actually needed to send into the MPLS network because maybe they wanted to communicate with the MPLS VPN devices. So how to do? What to do? We can use GIE to solve that. We can use the GIE to solve that. And working like this. In this PE, here we use MPLS VPN. We can use MPLS VPN tunnel. And in here, the internet, we can create a GIE tunnel. We just put the GIE tunnel and the MPLS VPN tunnel in the same URF, then the route can be forwarding to each other. So those devices, those network can communicate with each other, So this is another using scenario. Okay, especially when you're trying to combine two different networks between the internet and between the MPLS, you can use this. Okay. Okay, so let's continue. This is for GIE, and then let's look at the L2TP. L2TP, as we said, it's VPN. It's an access VPN. It's an access VPN. So VPN for the basic architecture looks like this. We have those type of 3 devices: NAS, network access server; LAC, connection access concentrator, and network services. Okay, so also there are some architecture is a tunnel, L2TP tunnel. And inside the L2TP tunnel, we actually have L2TP session because there can be multiple sessions forward inside the same tunnel. Okay. So let's look at the message structure for the L2TP packet first. So for the L2TP packet, there will be 2 types of packet. One is for the control, another for is data forwarding. So control message basically exchanged between the LAC and the LNS, and for the date message, most of the time it's a PPP packet. It's a PPP packet. So it's why it's called L2TP. Those PPP, they are using PPP as a layer 2 protocol. L2 is level 2, right? Okay, anyway, look at the working principle of the L2TP. Simple. They basically have 3 steps. First is establish L2TP tunnel, then L2TP session, then transmit the PPP packet. There will be 3 steps for the L2TP. Okay. First, they will because if you want to create an L2TP tunnel, you need to input password and username and password. So the device will try to create a call connection and put the password, username to the NAS, LAC. They are in the same device, and this NAS will try to like detect whether this password username is okay or not. Okay. And after that, the NAS will try to create the connection, the L2TP tunnel, the tunnel with the LNS. So if you configure the IP address for the LNS, it will directly create the connection. But if it is not based on the domain name, and they will ask from the DNS for the LNS IP address. And after the tunnel is established, they will discussion. They will try to create. They will try to negotiate a session number, and then they will create the L2TP session. We establish a established session, and they will go into the negotiation. There will be some certain negotiation for the PPP, like you know the PPP steps, like LCP, NCP, those kind of information. And you actually can do a real authentication, but well, it's optional. And then the LNS will allocate the IP address. They will assign the IP address for this enterprise, and then they will communicate. Okay, 3 steps basically, simple one for the L2TP. So L2TP can be used in many scenarios. First is for the mobile office. For example, there are some employees going to the business trip, and so this one can be used to connect back to the enterprise. And also can be used to create the connection between the branch and the headquarters. Also can be used for the L2TP. So basically, you put the one client in the one side, another in another side, and create the L2TP tunnel, and write down some root entry, and you can go to our side. Here's some other scenario that if some devices inside and it creates a PPPoE to the L2TP. Also can the PPPoE also can be carried here. Okay. So this is for the networking technology. Okay, common networking technology in the WAN interconnection. Any question so far? Okay, so let's continue. This is a very simple one. We just continue. Let's talk about the IPsec, the security technology of the WAN interconnection. This also is a key technology for the WAN interconnection. So IPsec is important. We know because IPsec can encrypt the packet. So when the packet forward above the internet, even the packet is being captured by some other people. The people cannot decrypt the packet, decrypt the data. How is the L2TP achieve that? Sorry, how is the IPsec achieve that? Okay, there will be some way to do it. So there's a overview. So we can see the IPsec overview is like this. First, in the one side of the IPsec, they will encrypt the packet. They will do the encryption and the authentication for the data. And when it's sent out to another side, and the data will will do the decryption and we'll try to do the authentication again. Okay. So what is the working principle of the IPsec? And before we talk about the working principle of the IPsec, first we need to have the concept of the encryption, because the encryption is the key, is the core technology, the core concept of the IPsec. So what about the encryption? In this world, there will be two types of encryption. One is called symmetric encryption, another is called asymmetric encryption. What is symmetric encryption? What is the good side about it? So the symmetric encryption means I use the same password to do the encryption and to do the decryption. Simple, right? So the good side about the symmetric encryption is that it's highly efficient to do the encryption and the decryption because I use the same password. That's all. But there will be problem. The problem is about key exchange. How can I exchange the key? You may be thinking, okay, I can directly forwarding from one side to another side. I will send in the packet for the key. But if, in case, if your key is being captured, then which means your encryption and decryption means nothing. I can encrypt it, I can decrypt it, because the hacker have the key exchange. Have the key. So this is a problem for symmetric. The symmetric encryption very efficient, but there's not a very security way to exchange the key. This key will be used to encrypt and decrypt. So there will be another technology called asymmetric encryption. Asymmetric encryption is they are doing this way. They will generate two keys. One is called public key, another is called private key. For example, at route 1 sending packet to route 2. Okay, and those two public key and private key, they actually have some relation between them. They are related, but you only have private key. There's no way you can calculate out. You can know the public key. There's no way. So then the router 2 in this picture, they were sending the public key to the router 1. So when the router 1 trying to send in packet, router 1 will use this public key. The router 2 gave router 1 this public key to do the encryption, and I send out to another side. And when it came back, I will use the private key to do the decryption, and I will get the data. Since if you only get a public key, there's no way you can get the private key. That will mass problem. I mean, not messy, that mass, M-A-T-H, that mass, the number. Okay, there's mass problem. Because there's some mass, it's called a big number problem. That means you have some special number that if you multiply them, it will be okay, but you cannot divide them again. Okay. Anyway, it's a mass things. Okay. There's some formula here. So anyway, let's continue. So you can see the asymmetry actually is very secure. It's very secure, but the decryption for the asymmetric encryption this way, it's low efficient. The decryption is very slow. Okay, so this in this world we have two ways to encrypt. And another concept we need to know before is data authentication. The data authentication is also very simple. It's just when the packet is sending out, before they send out, they will do a hash. They will do the hash, and the hash will create a value, hash value, and it will be attached after the date and send out. And the data will doing the hash again, and to see if this hash number and this hash number is even or not. They will compare them. If it is not even, it means this packet is being modified. Okay. So what does IPsec do? What does IPsec do? For those kind of information we have, what does IPsec do? The IPsec must first need to guarantee security for the packet, and second, IPsec should be efficient because we are in the network. We want the devices to process the packet much more efficient. So the IPsec is in this way. First, the IPsec will use the asymmetric algorithm to encrypt and transmit the key, and this key will be used for the asymmetric encryption, and users exchanged before it is exchanged the symmetric key to encrypt and decrypt the data. So it's like this. First, use asymmetric key to forwarding the symmetric key. And this symmetric key later will be used to do the symmetric encryption. Okay, to encrypt and decrypt the packet. Okay, right? Simple idea. Okay, so we can see that when we do the encryption and the decryption, and there will be a lot of choice, like which key you are using, which algorithm you are using to do the encryption, decryption, to do the authentication, and for the IPsec VPN, you should use the tunnel model, transmit model, etc. That will be some how do I say, there will be a lot of parameters we need to set for the IPsec. So how to set it? Okay, and first we need to have the concept of SA. What is SA? Security association. It is this different elements, combine them together. It is SA. Okay. So if you want to create the IPsec traffic, if you want forwarding IPsec traffic, at least you need to let the other side know that okay, you are using which kind of way to do the IPsec. Okay, so you need to send in the SA to another side, or send in the SA information to another side, or you need to negotiate like with the other side. So how to exchange the SA? We have some technology protocol called Interconnection. net key exchange. We can use that to do the negotiation. So the Internet Key Exchange, IKE, is a very important protocol. This can help us to exchange all kinds of assay information, and also inside of this assay information, there will be the symmetric key also will be use IKE to forward us. Okay, so IKE packet UDP destination UDP 500. Okay, port. Okay, and for the IPsec, they are using IKE to exchange the key, to change the symmetric key, and after that, they will use a symmetric key to do the encryption and decryption. And when it do the decryption, they also needed to do the authentication. So it's like this way. Some packets, they are using the symmetric key. This symmetric key is being exchanged by this IKE in this SA negotiation. It is exchanged. And they will do the encryption and send out the packet is encrypted, and when it reaches to the other side, when it is forward out, they will also do the hash, and this hash will put in the tail of the, put behind the packet and send out. When it's to the other side, it will do the hash algorithm to calculate and trying to decide whether those two hash number is even or not. If it is even, which means it is consistent, I will process and I will trying to decrypt the packet and send out. Okay. So let's talk about a little bit of detail of IPsec. And for the IPsec, when you do the forwarding the packet, we actually have two header format. One is called H header, another called ESP header. The header looks like this. And let's not jump too much detail into this header format. Let's talk about the function for those two header format. First, the H header only provides the authentication function, which means if you are using IPsec H header, those kind of way to encrypt, to encapsulate the packet, this packet can only be used to authentication. It cannot be encrypted. And ESP can do both encryption and authentication. So in the real network, most time we are using ESP. So this is encapsulation mode, and we have two types of encapsulation mode. One is called tunnel mode, another is called transport mode. So let's talk about the difference between the tunnel mode and the transport mode first, and we can say that tunnel mode means you will put a new header before the IPsec header. You put a new header. And the transport mode means I will still use my old header, old IP header to do that. Okay. So when I should use tunnel mode, when I should use transport mode, very simple idea. That, for example, there will be a PC here. There will be a router which I will be used to create the IPsec tunnel, and another router. So between them, you create IPsec tunnel, and then another PC2. So when you're gonna use the tunnel mode is when the PC1 wants sending to the PC2. Those IPsec mode you should set to the tunnel mode, which means the generation point of the packet is different from the south tunnel point. tunnel IPsec tunnel source device and the packet generate device is different in different places. You should use tunnel. For example, here, PC1, PC2, they are not the source or destination for the IPsec tunnels, but between them they wanted to put in the packet, so you need to use the tunnel mode. So in the other hand, if these devices just want to communicate with these devices, and these two devices also happen, they are also the source and destination for the IPsec kernel. So under that circumstance, you can use transport mode. Okay, so basically most time we are using this. Okay, so here is a basic concept of the IPsec. And let's look at the IPsec fundamental. And okay, so IPsec mechanism, the working mechanism is like this. So first we will use the IKE module to exchange the SA. This SA is what for? It is for like the main usage for this IKE SA negotiation is to exchanging the symmetric key. And after that, in the IKE phase 2, the IPsec will use the SA information. There's a little bit problem with what I said. First, they will exchange the IKE SA. The SA means those two devices, they will use which kind of way to do the encryption, decryption, authentication, those kind of things. And in the second phase, here's the problem. In the second phase, the IPsec will use the IKE SA to do the asymmetric encryption, and they will put the symmetric key here and use this IKE SA to do the asymmetric encryption and put the key inside this SA and forward out. Not inside this SA. I mean, use this IKE SA asymmetric encryption and forwarding the packet to the other side. And then both sides will have the symmetric key, and not just the symmetric key, also like how you're gonna do the encryption, encapsulation, how you to choose the header. All this is SA information. They will exchange with each other. And then based on those IPsec SA, the user state will try to do the encryption and authentication and send it to another side. So here is a big picture, and let's look at a little bit detail. First, let's talk about the IKE. IKE have two versions, version 1 and version 2. No matter which kind of version it is used, the IKE have two jobs need to be done. First, they need to create an IKE SA. This SA will help us to do the asymmetric encryption, and those asymmetric encryption will help to exchanging the symmetric key, which will be used later to encapsulate, encrypt, and decrypt the packet. Okay. Anyway, phase 2 is exchanging the symmetric key, not asymmetric key. Okay. So the whole procedure basically looks like this. I will briefly talk about it. Okay. So main mode, there will be 6 steps. The first 4 steps, they are trying to exchanging the IKE phase 1. They were changing the IKE SA. And then the 5 and 6, those 2 steps is trying to exchanging the IPsec SA. Trying to exchange that. So this is main mode. Another is aggressive mode. Aggressive mode is when I exchanging the like symmetric key, when I exchanging the SA information, I will use the plant number. I will use a plant packet. This is aggressive mode. Okay. And then let's go into the phase two. So the phase two is like this. The phase two is trying to exchanging the symmetric key and other information related to IPsec SA, related to the IPsec, for example, whether I should how do I say this? Like whether I should use tunnel mode or I should use the transport mode, like I should use H header or ESP header. This is all being decided in this quick mode. Okay, this is phase two. After the phase two, both devices will know the IPsec SA for the other side. So they will use the SA information and trying to encrypt the packet and forward to the other side. Okay. And there will be another version, IK version 2. So IK version 2, you can see it's simpler than the IK v1. First, there will be only two steps for the initial exchange. 2 steps. First, the 2 steps, they will exchange the SA, IK information. Then, for the initial exchange, it will be okay. Then it will sending for the identify and information. Okay. And after that, you actually already created the IPsec kernel. Okay. And for the IKv2, when you trying to create some other IPsec kernel and use the same IKE SA information, then you can just use this create child SA exchange process to create another, to exchange another SA. Also is okay. Some information exchange, like performance or something. Okay. So after you create the IPsec kernel, you need to lead the packet. You need to lead the packet into the IPsec kernel. So how to do it? There will be 2 ways. First, you can use ACL. Another, you can use the routes. ACL means like you can define which traffic should use the IPsec kernel. And use routes is if I want going out from certain interface, all the traffic going out from this interface, I will encrypt it. Oh, okay, it's like this. Okay, so here is IPsec fundamental, the basic idea for the IPsec. Then let's look at the IPsec application scenario. Okay, first is GRE. GRE we talk a lot, so we just look at it. It will be okay. So first, the GRE of IPsec packet in transport mode and internal mode, we can say it's the packet will be different. So this is for the transport and private IP, GRE, and public IP from here to here. And if you're using 2 kernel mode, the private IP is here and here, and the GRE header, and the public IP is here and here. And also we have another public IP is also here and here, but this is tunnel mode. Right? Tunnel mode is working like this way. Another, this is another unit scenario is L2TP. L2TP. Similar with GRE. So let's continue. Then let's look at the IPsec NAT traversal. We will talk about another traversal later, but here we check the IPsec NAT traversal first. Since in the network that there will be problem with IPsec trying to, when two devices trying to create the IPsec tunnel through the NAT devices, they got problem because the NAT devices will how do I say, will changing the out header, changing the out header. So there will be the authentication problem. There will be an authentication problem. So the H first for the the H will authenticate the whole packet for the H. So if the, no matter you are using kernel mode or you are using transparent mode, the out header is exchanged. And since H is do the authentication for the whole packet, so the out header, if the out header changed, the authentication cannot be passed. So which means I will discuss the packet. So the H will not being used in the IPsec NAT traversal. So another one is ESP. ESP, they will only do the authentication in this ESP header, and out header, the ESP will not do the authentication. So this ESP is okay. It can be used, have the potential to do the NAT traversal for the IPsec, but ESP also had its problem because when we do the configuration, two devices, if they wanted to exchange the IPsec SA, they also, between them, they also need to do the authentication. This authentication means, okay, it is you. If it is you, I will receive the IPsec SA. But how to define, how is the gateway define the gate 1? Gateway 1. How did I know this gateway 2 packet received is from gateway 1? Okay, so for the IPsec kernel, they will use their IP address to do the authentication, to see whether this IPsec sending to me, IPsec SA sending to me, whether it is allowed to send to me or not. Then there's a problem. Since I was go through the NAT devices, the source IP address is of course different. Of course it is different. So the gateway 2 cannot know whether this packet is from gateway 1 or not. So what to do? The solution is like this. So first you need to changing the destination UDP port to 45000, because we know the IKE exchange packet by default is 500, but if I use 4500 to, and the other side will know that, okay, you are behind the NAT devices. So it will be very easy to for us to, like, how do I say this? Well, easy for the devices to know like you are behind the NAT or not. So here is some example, like whether I should change the key to 4500 or not. They will do the detection to see like whether you are behind the NAT or not. Okay. So when the NAT device is detected, its cap will change the source UDP port number from 500 to 4500. So if I use this port sending to the other devices, the other side will use the what you call the username to decide based on the name to decide whether this gateway is allowed to send in the IPsec SA to me or not. Because before they are using based on the IP address to do the authentication for those two devices. But if I detect that you are behind the NAT, I will use the name to do the authentication. So some using scenario. Let's quickly look at it. Okay, that some scenario. Just pass some NAT services. Okay, this is session keep. Pass. So basically, we have a basic idea of like how is IPsec NAT traversal want to do. So basically, two things. First, allow them to detect whether there's an NAT or not. If there's an NAT, they will change the port for 400 to 4,000, from 500 to 4,500. And after I know the other side have NAT devices, sorry, I will use the name for the devices. When I do the configuration, you can configure name. Use that name to decide whether I is allowed to receive your IPsec SA or not. Okay, so this is IPsec NAT traversal. Any question for the IPsec? Okay, so let's take 10 minutes break, then we will move to the NAT traversal and intelligent traffic steering technology. Okay, so let's continue. Let's finish the last two parts. Let's first we talk about NT traversal, and then a little bit intelligent traffic steering. Okay, so NT traversal first. Okay, so we know in our network there will be a lot of NT devices, because with NT devices, it will be able to help us to provide, to connect the private network and the public network. We need the NAT, right? So there will be a little bit basic idea of NAT. NAPT. This one I guess everyone is familiar, right? NAPT. What is NAPT? What is easy IP? I guess this one is easy. We just mapping the private and IP address port to the public IP address port. Will be okay, right? So about this we pass. It's very simple. And the NAT server, I guess everyone is also very simple, very familiar. We just mapping a port outside like 8080, and if any packet ping this IP address and the port, the NAT devices will send it back to the inner network. Okay, and besides that, there also will have some other NAT basic ideas that we can use the IP address pool for the NAT network, right? Because one NAT IP address only can mapping this number of the port, right? This is total number, total port. Actually, this is 5. Those is the port we can mapping. This is all the session we can do the mapping for one IP address. So most of the time we will do like we can do address pool to provide like more session, to support more NAT session. Okay, in some special scenario that like if you are using the NAT port and your NAT devices is not egress devices sometimes. Okay, so when the traffic going out from here and when it come back, maybe it will directly go like this way. So it will got problem. So if you create an NAT pool, you can check your devices. It will automatically create a router called UNR router, user network routes. So user network routes basically is a 30 host routes. The host routes related to the NAT pool. So with this host routes, the egress will know, okay, if I want sending the packet back, I should send it to the R1. Okay, this is some basic idea for the NAT. Okay, so we know that the NAT like a basic working principle, right? When the packet from inside to outside, it will create a session in the mapping table, right? And this mapping table will exist for certain seconds, and after that, this table will be erased. And if the packet always go out and come back, go out and come back, this mapping table will be always exist. And there will be a problem. There will be a question here that if since I created a map table here, when inside the packet is sent out and it will create a table, the outer header is IP is here and a port is here. If there's some external host, maybe it's an attack or something, is sending the packet to this IP address, to this port, if somehow I know the port and IP address for this session, and I sending the packet to this IP address, to this port, should the NAT devices boarding the packet in or not? This is a question, right? This is how, actually this is how NAT works. So let's look at whether this will be or not. So if the external host doing this way, based on the created session, I will use this public IP endpoint, use a destination IP endpoint, and send back whether I should the NAT devices forwarding into the internal network or not. It based on the NAT types. This NAT types is not what we called like the NAPT, the static NAT server is not that. The NAT, this is the type for the source NAT, the type for the source NAT. So before we talk further about the type of source NAT, we need to define some basic concept. Is tuple. Tuple. We have we divide our network. We can describe our NAT network into 3 types of tuple. One is internal tuple. Internal tuple means I have a IP address, I have a port. This is the packet. This is a inner packet, the source IP and the source port. And also we have a target tuple. Target tuple is where I want to go. This packet, where this packet want to go. They have a destination IP, destination port. And when I go through the NAT devices, we know the source IP and the source port will be changed by the NAT devices. So this changed source IP and the source tuple, source port, we call it external tuple. Okay, so we define the 3 types of tuple first. Easy for us to how do I say this? To describe the NAT types. Okay, so let's look at the NAT types. This is for the source NAT type. Okay, source NAT type. There will be 4 types of source NAT. One is called full core NAT. Full core NAT. Full core NAT is working like this way. If there's a packet I send out, and this packet create a session, source, private, the internal tuple, external tuple, target tuple looks like this. And there will be an external host. No matter this host source IP address is what or not, this host I sending a packet, destination is this, destination IP, destination port is this and this. It's equal to the external tuple, and the packet sending to the NAT, the NAT devices will send in the packet into the private network. This is called full core NAT, full core source NAT. Okay. Another is called restrict core NAT, or you also sometimes you will see this as a restrict IP core NAT, same thing. It means that when I send in the packet out, and I was have source IP, internal tuple, external tuple, and target tuple. And if I want sending the packet into the private network, I must create a packet. Our source IP address is this, and the destination will be this and this. If my packet, this external packet, is fulfill this need, this packet will send in. Okay, restrict call. And another is port restrict call. Okay, port restrict call will be working like this way. Is that the port restrict is like this. First, I still sending a packet out, and I will create internal, external tuple, target tuple. And this external host, if they want to send in the packet into the private network, the packet this host create must be like this. IP source port must be equal to this, equal to target tuple, and destination IP endpoint must be equal to this. Then I will send in. So port restrict call NAT. And the last is a symmetric NAT. Symmetric NAT will be working like this way. So it means that different session, they will have different will have their private IP and port may be same. Their source IP and source port may be same, but I will create a different external tuple. Even they have the same source and port, same source IP and same source port. I will create different IP address and port. So it will be difficult to send back because I needed to know like which IP you are using. Okay, symmetric. So why we need to know the source NAT type? That will be related to our NAT traversal. If we are using CORN type, including full CORN, port restrict CORN or restrict CORN NAT, those type of NAT can create a NAT traversal. And this NAT traversal is much more common. The using scenario is very, very common, which means in all the scenario, as long as your NAT devices is using the cone type source NAT, those two PC, no matter which traffic I'm sending, I can communicate with each other. Okay, so let's look at the NAT traversal technology. Okay, this requirement is very common, that two devices, they want to communicate with each other. So without creating the GRE internal, I want to directly communicate with each other. That's where the NAT traversal can be used. So in the most of the time, the NAT traversal will use two technologies. One is ALG, another is STAR. And IPsec also will be used. IPsec NAT traversal, that technology also will be used. But here we, because we talked about the IPsec NAT traversal before, now we only talk another two type of NAT traversal technology. Aggregation ALG application level gateway, and this session traversal utility for NAT 2 type. Okay, first is NAT ALG. NAT ALG will this NAT ALG is especially they are used for those have what do we call it? We have a multiple channel protocol like FTP, DNS, SIP, those kind of multiple channel protocol. Well-known multiple channel protocol. Okay, well-known multi channel protocol. Okay, the ALG were used for that. So basically, mounting channel means you create a first channel and then you use this channel to discuss what is the rest of the channel, how to establish the rest of the channel. So the ALG have a very simple concept is that I will try to I will try to listen. I will try to listen the packet you for those kind of protocol to find out what is the next channel those protocol will use and create some NAT, automatically create some NAT mapping table and allow them to go inside. This is NAT ALG. So here's a little bit of example for the NAT ALG. This is for the FTP, a very common using scenario for the NAT ALG. So it's like this. Because we know that by default, the FTP will use port 21 as a uh, as a control channel. So this port is fixed. We will always use 21. So we will put the NAT. We'll create an NAT server, this feature here, and allow the this PC IP1 to communicate with this IP4 FTP server. And then after that, because I use a passive FTP, the passive FTP means that the server will wait. They will wait the IP1 to establish the FTP transfer data channel. So before they transfer the data channel, they will exchanging the FTP control channel, and the IP1 will tell the IP this PC will tell the FTP server that I want to use which port to communicate with you. Okay. So during the exchanging the FTP information, these NAT devices, if they enable the NAT ALG, they will listen. They will know that later the IP1 will use 1025 to sending a packet to the FTP server. So it will automatically create a session, and when the packet reach to the IP3, since my destination is IP3 and is IP since my destination is IP3, my destination is 1025. This is the IP3. This device is listening, and the IP3 will send into the IP4. We're sending to the IP4. Okay, so this is NAT ALG, but NAT ALG have a usage limitation. I mean user scenario limitation, because there's some disadvantage for the NAT ALG. First, NAT ALG needs to read the protocol package. So for new protocol, or maybe this is private protocol, the NAT ALG do not know, because it is new. I don't even know like this protocol how this protocol works. So NAT cannot do it. Only the well-known protocols, the NAT ALG can work. And also, not all the devices support this feature, NAT ALG. So if you want all the devices to support this, it costs a lot. And the third is that NAT solve the problem facing multi-channel protocol in NAT server scenario. But if this communication between the host, but does not support the communication between the host on the private network, it's only for the multi-channel it will be okay. But there's a lot of protocols. Traffic is not multi-channel protocol. It's just two devices behind the NAT devices. They want to communicate with each other. This is only this kind of requirement that NAT ALG cannot fulfill. So what to do? There will be some other technology for the stun, called stun. So first, let me make it clear that the stun is not a technical can help us to directly to do the NAT traversal. The NAT stun right now is just used to do the detection. To detect what? To detect whether you are whether this devices is behind the NAT server or not. And also will know what is this site, the IP source, private IP and port, public IP and port. This is stun wanted to find out. And after I know those kind of information, there will be a very easy way to create a kernel, to create a mapping table and allow them to pass. So the working principle for stun is very simple. That before they want to go into the network, they want going to if they want to achieve the network net traversal, the stun client will first send in the packet to the stun server. This is some devices located in the public IP network. Okay, this must be public IP network, and this stun client, they will send in a stun binding request. Inside of this binding request, there will be an IP address for itself. This will put into here. And when it send out, of course, the source IP and source port will be changed because I was pass NAT devices, this packet pass NAT devices, and send into the stun. And stun will detect, okay, it will detect that what is your source IP endpoint, source IP endpoint. And this source IP endpoint is being changed by the NAT devices, and the stun server will put this IP endpoint into this binding request response and sending back. And this NAT devices will switch this IP endpoint port back to the original one, back to the original one. Okay, then the stun client, they compare the IP and port and compare to the stun bind request. They will response. They will know. The stun will know. Okay, first I am behind the NAT devices because those two IP address is different. Secondly, they will create some kind of mapping information for IP1, port 1, IP2, port 2. Then later, this information can ask the stun server or some other devices to forwarding this information to some other devices. So these devices, based on this information, can send in the packet into the private network. So this is the stun works like. It works like this. Okay. Wait a moment. Let me check something. Okay, so this is for stun. So we can say stun is not to create a network traversal. It's just a detection, but detection is important. So here's some application example for stun. So basically, for example, if two stun clients they wanted to communicate with each other, they were sending the stun request to the stun server and ask the stun server to, how do I say this, to tell the stun client whether you are inside the behind the NAT devices or not, and the packet you send out, what is the IP and port is switched to, okay, and so all the devices will know, and then this stun client will forwarding those kind of information to the other side. They will forwarding to each other. They actually forwarding to a stun server, and stun server forwarding it actually. But anyway, now the stun client know that this stun client, this IP4 stun client, it's a public IP endpoint. So I will use this public IP endpoint and send it to here, and this devices will sending back to stun. Now the stun client can communicate with another stun client. It's working like this way. Okay, so this is NAT traversal. This will be this technology will can be used much more widely. Their usage is much more widely. They do not require uh, to read the packet for certain mounting channel packet. Okay, so this will be much more easy, and the using scenario will be much more wide. Okay. Okay, so this is a NAT traversal technology. Any question? Hmm. Okay, so let's look at the last one. The last one is intelligent traffic steering. We talk about the SAC and the SRP. Those two actually we talk in the in the last slide. We already talked about it. So here we briefly check it about the SAC and the SRP. So this is for the so if we wanted to do the intelligent traffic steering, the intelligent traffic steering means based on your traffic application requirement, I will switch the path. And based on the path, based on your uh, application, based on the application requirement, and based on the uh, links quality, network quality, I will try to select the best path. Okay. So SAC is only for one purpose, is trying to classify the application, recognize the application. So with this SAC detection, it will know it is which kind of services, which kind of application it is. Okay, then they can do a different thing. Okay, so how to recognize the traffic? We will go through the signature database. So this picture we actually already talked about before, like how to go through the signature. Okay, how to identify the traffic, how to identify the application based on those two databases, FPI and SA. And there's a little bit example, a little bit of detail of SA. So this SA, it actually based on the this database. Inside database, it looks like this way. It's based on like this packet destination IP address, based on domain name, based on the protocol. They will define like which kind of application this traffic is. Another is FPI. FPI is called the first packet identification. Use this based on 5 tuple information like source destination IP, source destination port, protocol to define the traffic, which this traffic belongs to which application. So why we need FPI? Why we not just put all the things in SA? For 2 reasons. First, if we want to use the SA database, it means we need to read a certain packet. Then we know, okay, those traffic is, for example, it's a Twitter traffic. But if it is not Twitter Twitter packet, so which means the first 2 packet maybe is some virus or something. Then you let them in. You let them in. You will got problem. Or maybe you let them out. Okay. So the FPI will be, because it's based on the first tuple, the first packet, it's based on 5 tuple. So the first packet, they can already detect what is this traffic, what is this traffic, which kind of application this traffic belongs. But FPI, you need to write it by yourself. Okay, it's not predefined. SA database is predefined, but FPI is not. But the FPI have another advantage is that some application is a private application. For the Huawei, there's no way to know the feature for the private application. There's no way. So this SA will not work because this is only for the well-known, the public application. But if for some private application, you need to use FPI to do that, to detect, to define which traffic it is. Okay, so after we classify the application, we classify the traffic. We know which application traffic belongs. We can use this SPR, smart policy loop, to change the path, to control the path. And this we actually also talked before. We use NQ IP FPM to detect the path, to detect the network quality, and use this information to decide this application should go this path or should go this path. So you can see. Okay. So here is how is SRP to do the link selection. Here I will not talk about details. Basically, you know there will be some selection process. There will be some selection process. There will be some way to calculate it. Okay, this is how we use NCE to implement SPR. Okay, so like in the campus, we actually in NCE campus, we just learned they have this SPR to control if the traffic going out from the campus, like which path they should choose. Okay, then let's do some quiz. First question: which of the following are private LAN technology? Okay, SDH, MPS. SPR technology can be flexibly select the egress link based on the link quality. True. Okay. Summary we pass. Okay, that will be all. That will be the whole information for the key technology of WAN interconnection. Any questions so far? If you have a question, no? Okay. Okay, so I guess if there's no question, yes. Yeah, Mr. Lois, you want to ask me anything? Okay. Okay. What's the difference between NQ and IPFPM? Okay, let's move into that slide. It's in another slide. NQ and FPM. It's like this NQ, where's NQ? Here. Okay, NQ is working like this way. For example, I want to detect the HTTP this traffic. I want to detect whether this traffic can forward in a good way or not, like whether they can forward in a low latency, there's a low packet loss rate. Well, I want to detect how is HTTP traffic forwarding in this network. Okay, what is the NQA do? The NQA doing like this. When the NQA doing test, they are nothing related to the real traffic. The real traffic is forwarding between the NQA and between inside this devices, inside this network. The NQA, how do I say? They cannot do a test. They don't know. So how is the NQA to detect the network whether this HTTP traffic is okay or not? The NQA doing like this way. In this NQA client, they create some HTTP packet. This packet even, it is not a real traffic. It just creates some HTTP packet and send out. And going to this NQA server, this NQA server will be used as a HTTP server. And it will reply, and send out, and reply. That's all. Then the NQA client will collect those kind of information and to do the calculation to check whether those HTTP packet have the packet loss rate or not, have the what is the latency, does it have a very bad jitter or not. So you can say the NQA test is nothing related to the real traffic. They only create their own traffic to do the testing. Okay, it's like someone is running. You wanted to know whether this this path is very nice, feel very good to run, and you run by yourself. But the feeling of yourself and the feeling of other people is different, right? So which means the NQA testing, the result for the NQA testing is not accurate. I guess this is easy to understand, right? So what is IPFPM do? The IPFPM doing like this way. I will put a number into the real packet header. For example, this is also a web header, is a HTTP packet. When it sent out by these devices will put a number. We call it color, but basically it's a number into the IP header. Because we know that in the IP header we have a field called TOS, type of services, right? The TOS only use the first 6 bits, DSAP, right? We only use the first 6 bits, and the last 2 is not being used. Actually, last 3 bit is not being used. We only DSAP, as I remember, only use the first 6, but we can normally just use the first 5. The last one we can put into 0 most of the time. Anyway, we are put a number into the IP header, so which means I color it, and when it send out, this is the ingress, this is the egress for the network, and it is sent out, and and this port will record like how many packet with this number. For example, this is number 10. This is also number 10. How many packet be marked as a number 10? How many those packet is go out from my interface? So and these devices will record how many packet with the number 10 packet is into the network, and they will report this information to this MCP, and the MCP will do the calculation, like how many is in, how many is out, and what is latency when enter in, what is time when enter out, what is time. Like for the first 10 packet and the second 10 packet, what is latency, and for the third packet, which is latency. So based on those kind of information, you can calculate the packet loss rate, calculate the latency, calculate the delay, to calculate the jitter. And you can see this color is being marked to the real traffic, which means the network situation you get, you use the IPFPM to do the testing, you get is a real uh, result. It's not simulated by the IPFPM or something. This packet is actually is actual services traffic. So use IPFPM, it will be much more very accurate to detect your real network situation. So this is different between the NQA and the IPFPM. Hmm. Hope this explanation will answer your question. Okay, any further question? Yes, only use the to check the network performance, that's all. Yeah, if you want to change the path, we will use we use this, where is it? We use this SPR, smart policy route. This one, smart policy route. The smart, yeah, yes, smart policy route. Use this one, you can change the path. You can change the route. You can change where I should go. But the IPFPM just to detect much more accurate. Yes, we also can use like because IPFPM and NQ basically just do the detecting, like detecting the detect the quality of the link. That's all. You can use the NQA and with the SPR together. There's no problem because no matter IPFPM and NQA, what they do just to have a result like what is quality for this link. And this SPR, sorry, I maybe have some typo. This SPR is this feature is will use the result for the IPFPM and the NQA to decide okay whether I should go which path. Yeah, IPFPM must use SPR. That is correct. That is correct. But I guess for the Huawei devices, I don't know whether they can use NQA to do the if and then to do this. I don't know whether we can or not. For Huawei, I don't think I have seen this kind of configuration for NQA. Hmm. NQAI. Okay, any other further question? Do you have WeChat? My ID is Luis Man. Sure. No problem. Luis Man. Okay, so how about the others? Do you guys have any question? Okay, so if there's no further question, I guess that will be all for tonight. So, I mean, in China it's night. Okay, anyway, so see you tomorrow. See you guys tomorrow.